Hi everybody, pre-calculus. Here we are in section 11.2, and we're going to be talking about exponential functions. So exponential functions, first of all, when we talk about exponential functions, and you may have seen in our Algebra 1 series, we talked about exponential functions as y equals a times b to the x, where a could be just like a coefficient of any of the functions that we've talked about. Sine function, coefficient of ax squared plus bx, like the lead coefficient in so many functions. Our text chooses to leave a out and really just study y equals b to the x. I'd like you to keep in the back of your mind that we could have a coefficient of the function that we're going to be discussing, this guy, y to the b to the x. We could have this coefficient a such that a would do what all coefficients do. The lead coefficient either has the function reflected over the x-axis because of the sign if it's negative, or it could stretch it vertically, it could compress it vertically as well. So I want you to keep that in mind, but let's just focus on this function for today. So we're going to talk about power functions. A power function is when you have like y equals x to a power, so x to the fifth. And we've studied these when we're dealing with polynomials. We know y equals x is a line, y equals x squared is a parabola, and y equals x to the third power is going to be a swoop-de-loop. And then all of these guys will kind of continue on this wavy pattern, right? These polynomial formula movements. So this is considered a power function, the simplest of exponential functions, of polynomial functions in a sense, all right? So a power function has x being raised to a power, while an exponential function has a number, a positive value, a positive number that's not 1, being raised to the x power. So let me write a little restriction for you. B has to be greater than 1, and you're going to see it down here in this box. B has to be greater than 1, because otherwise we'd be raising some negative number to a bunch of different powers, and that would be very weird. Think about what that would look like. Think about a -2 raised to the second power. That's a +4. But then a -2 raised to the first power. That's a -2, and you're not going to get a continuous function. So we restrict b to being positive, but also b cannot equal 1. So b has to be, I should say positive. That's not it. B has to be positive. Stay with me, babies. And b cannot equal 1. That's how we'll define it. We'll talk about the characteristics down here. Exponential decay. So when you have something going down in its amount over time, you would have this b value would be between 0 and 1. Let me write it like this. If we wrote it in interval notation, it would be somewhere between 0 and 1, not equaling 1, right? Or we could write it like we have here. So when that's the case, b is some positive fraction. You can think of it that way. So y is equal to b to the x would be something like y is equal to 1/2 to the x power. And you can see when you constantly multiply by a fraction that's less than 1, you're going to continue to decrease. Exponential growth will be the opposite. Your b value has to be greater than 1, because that's how you're going to get growth. Even if it's slightly greater than 1, you're going to get growth in that way. So y equaling some b value such that b is just greater than 1, 1.5 to the x power is going to be exponential growth. And so you have this chart where we're thinking about the characteristics of this particular graph. When b is greater than 1, we see that the graph is going to be increasing. We see that the domain is all reals. I can put any old x value in there. I can use, and we have this situation here. You can think about this. I can put any x value in here. I can, I'm going to see that all my numbers are going to keep growing. The range is going to be greater than 0, cannot be less than 0. The y-intercept, well, think about the y-intercept. When I plug a 0 in, any number to the 0 power is going to be 1. And you'll see that no matter what that b value is, right? We see that's going to happen. Here, the behavior is going to be continuous 1-to-1 and increasing. And there's a horizontal asymptote, and we'll talk about where that comes from. A horizontal asymptote, the negative portion of the x-axis, and a vertical asymptote. Let's think about what this looks like in terms of a graph. Let me give you guys a little bit of a view of what we're talking about here. So I'll get some space here and I'll draw a graph. So if I decide to graph y equals 2 to the x power and y equals 1/2 to the x power, I'm really fitting these two characteristics that they're talking about, b being greater than 1 and b being somewhere between 0 and 1, some fraction. And so check this out how we'll do it. We'll plug in 0 and we'll get 1. We'll plug in 2 and we'll plug in 1 and we get 2 in this function, right? 2 to the 1 is 2. 2 to the 2 is 4, brings us up here. 2 to the 3rd will bring us up to 8, which is about here. And you can see this is just going up and up and up and up. And as we move back towards the left on the x-axis, 2 to the negative 1 is going to be 1/2. 2 to the negative 2 is going to be 1/4. 2 to the negative 3 is going to be 1/8. And you can see this is getting really, really close, but it will never be 0. And you know what that relationship is. That's going to be our asymptotic relationship, right? I'm trying to make this look neat and I'm not helping out the situation, but you get what this graph looks like. Oh, on this side, things will be a little bit different. If I have 1/2 to the 0 power, I'm going to get 1, right? Because anything to the 0 power is 1. But as soon as I put it, if I work backwards and I say, well, let's try -1, 1/2 to the -1 power, take the reciprocal and raise it to the first power. So that's going to be 2. The reciprocal of 2 over 1 is 2. 1 over 2 is 2. And raised to the first power, you get 2. And already you might see what's happening. If I raise this to the first power, I'd be at 1/2. If I raise it to the second power, I'd be at 1/4. And you see what's happening. We're going to get that asymptotic relationship here. And let's see if we can finish this off. If I have a -2, 1/2 to the -2 power is really going to be 2 to the 2 power, right? Take the reciprocal, raise it to the second power. Oh, I'm up here at 4. And then similarly, 1/2 to the -3rd will bring me 8. And you guys see that we have a reflection in the y-axis in relationship to these two graphs. So that's what all of this is saying. Read through, make sure you feel comfortable with the characteristics of either graph. The formula that your text wants you to know in reference to growth and decay would be this guy. You start off with, you want to know the amount, n sub naught, or n naught is the initial amount, 1 plus r to the t power. Here, the rate is the r is the rate of growth or decay per time period. So if we are growing, this is going to be a positive value. If we are decaying, this is going to be minus. Therefore, 1 minus some value is going to bring us down to a fraction that is less than 1, but greater than 0. And then you can see we'd have decay. Whereas 1 plus is going to bring us to a value that is, or b value that's greater than 1, and therefore we'd have growth. Over here, compound interest, this is a great formula. The compound interest equation is this. When you are dealing with money and you put a principal amount in the bank, you're going to then be increasing that amount of money over time. That's going to be, you're adding the rate, and that rate over time is how you make money. If you compound the interest, not just yearly, but several times a year, n would be the number of times a year that you're compounding it. And therefore, you would not raise it just to the t power, you'd raise it to the t times n power. And hopefully our examples will illustrate that concept a little bit better. So let's look at our first example. Example 1 says graph the exponential functions, boom, bap, and bip, and let's see what happens. I want you guys to tell me what happens. If we have some function, if I start off with y equals f of x, and then I say graph y equals f of x, then graph y is equal to f of x plus 2. And then graph y is equal to some f of x minus 3. I would hope you know what this looks like. This is going to look like a shift, a vertical shift up and a vertical shift down for these two graphs. And I'm going to use Desmos. I'm going to employ Desmos to help us out with this one. So here we are on Desmos. We've got y is equal to 4 to the x. And just as we would suspect, we're going to plot, paste this down here. Let's see if I can. I'm going to copy that, paste that, and then I'm going to just add to it 3 and you see we shifted up 3, and then I'm going to paste this, and when I subtract 4, I'm going to do that. I don't even remember what we were adding and subtracting. Let's go back. What are we doing? Adding 2 and subtracting 3. My bad. Let's go ahead and do that. So if I add 2 and subtract 3, you see we just have vertical shifts that have occurred, and it kind of makes sense. It's just what we expected. So we see that the same rules for any function that we've had ever before will apply even to this new function. So now in part B, we are asked to graph the exponential functions, and in a sense we are considering, remember what we talked about before, y equals a times b to the x. We are considering these values almost as if the a value. And what happened before when we had an a value? Do you guys remember? When we have an a value, how does it affect the graph? You're going to see that it's going to do the same thing here. Let's go back over to Desmos and see. Okay, so you can see that y equals 1/5 x. This red graph is exactly what we had when we have like a fractional value raised to an x power. What do you think is going to happen with this 6? What's the 6 going to do? So this 6 it's going to be weird, but it stretches everything. It looks like it shifted it over to the right. I get it, but that's not what's happening. Remember, what we had here was 1, right? 0, 1 when I put 0 into the function, but when I multiply that function by 6, I'm going to get 0, 6. So it looks like a shift to the right. It's not. It really is a vertical stretch. Okay, so what do you think is going to happen here with this -2? We're going to have a vertical stretch, but it's going to move in the negative direction. So it is stretching. Again, it kind of has a shifting vibe, but it did not shift. It really did stretch vertically and then slightly, it stretched vertically and then it got flipped over the x-axis as we expect it to do. That's what we expect to happen when we fool around with the lead coefficient. So here in example 2, we're going to be talking about Newton's law of cooling, and the difference between temperatures of an object and its surrounding decreases in time, and that is going to be an exponential equation. So we're going to suppose that we have a cup of coffee that's 95 degrees Celsius and it is in a room that is 20 degrees Celsius. The cooling for this particular cup can be modeled by the equation y is equal to 75 times 0.875 to the t power, where y is the temperature difference and t is the time in minutes. So the first thing that we're asked to do is to find the temperature of the coffee after 15 minutes. So since t is in minutes, we know that we can simply, we're going to employ a calculator most definitely, we can simply take this equation, this formula, and for t, we're going to put 15. When we do that, we get 10.12 degrees Celsius. This is not the measure of the cup of coffee though, like the temperature of the cup of coffee. What this refers to is the difference between the cup of coffee's measure and the measure of the surrounding area. So now, before the cup of coffee had a difference of 75 degrees, now that difference is going to be 10 degrees. The difference is going to be 10 degrees. And so we can say that the cup of coffee would be about 30 degrees Celsius after 15 minutes. Okay, so we're going to graph the cooling function. Since this is the cooling function and it's best to graph on Desmos, let's head over there to get a graph for this. So after resizing my x and y axis to accommodate this graph, we see that the cooling function is as follows. Let me zoom this up a little bit so we can see after 15 minutes, which would be right around here, we can see that the temperature is about, the value is going to be about 10.12. The value of the difference will be 10.12. And the closer and closer we get, the longer time we let that coffee sit, we see that the temperature difference is really insignificant. So that's our function for that situation. So recognizing the shape of that function, we're going to do a quick sketch of the graph. So we knew that it was passing through the y-axis, or the y-intercept was 0.75, and we know that at 15 minutes, we know that we're about at 10.2, something like that. So I'm going to put this point here, and since we've got a logarithmic function, we know what it's going to look like. Something like that. Hopefully we can do a little bit better. When in doubt, make the line thicker and go quicker. There we go. Hopefully that's gonna, all right, that's it. That's my best. I should have just copied from Desmos, but you get what I'm talking about. All right, let's go on to example 3. This example comes from the text, and example 3 is like a real life one. So we're dealing with entomology. In recent years, beekeepers have experienced a serious decline in the honeybee population in the United States. One of the causes for the decline is the arrival of the Varroa mites. Experts estimate that as much as 90% of the wild bee colonies have been wiped out. The graph shows typical honeybee and Varroa populations over several months. A graph of the Varroa population with growth from April to September resembles an exponential curve. And so here's the thing. Even though in mathematics, even though things aren't exactly exponential necessarily, or aren't exactly fitting into, let's say this looks like part of a cubic or something like that, we use our information that we understand to make predictions. So even though the fact that this kind of looks like a bent line, it is sufficient to use an exponential function if we can get one to fit that situation. Right? And so here we are given some information that's going to help us do that. It says if we refer to this application, we're going to suppose that researchers can estimate the initial population of the Varroa in a colony is 500. So if that's the situation and we know that the colony increases at a rate of 14% per week, what is the expected population in 22 weeks? So this is going to require us to use that formula from earlier on. The amount is equal to the initial amount. Let me go ahead and get a normal pen tip. The amount is equal to the initial amount times 1 plus that percent increase. And so we write that percentage as a decimal, and then we're going to raise it to the time value that we know that this exponential increase happens, right? So we've got 14% per week. We're looking at T weeks. So in this case, T refers to weeks. And so we start off with 500. We want to know what we're going to have later on. We're going to multiply that by 1 plus 0.14 to the 22nd power. And so simplifying that a little bit, I'll put it under here. We'll get 500 times 1.14 to the 22nd power. Using our calculator, we get approximately 8,930 of these Varroa mites in that particular colony. That's the expected amount. All right. Okay. It looks like we have this example next, which is going to deal with some finances. So we're going to talk about compounded interest. And so we're going to determine the amount of money in a money market account, providing an annual rate of 5% compounded daily if Marcus invested $2,000 and left it in the account for 7 years. So we can reach back to our equation. We know that the amount of money we'd have that we learned above, the amount of money we have is equal to the principal times 1 plus the interest amount. Since this is 5% interest, we're going to do 0.5, and we could raise it to the T power. However, since it's compounded daily, what this means is that every day you'll get a part of that interest. So you'll get 0.05 over 360. So on the first day, you get a 1/360th of that 5%. If you only left it in the account for a day, you get what I'm saying? So therefore, it is not compounded just at the end of the year. It is compounded every day. So the number of years times 360. I would love to discuss this more if this feels kind of weird, but this is really a logical equation, and we can talk it through and it'll make good sense. All right. So with that in mind, let's see what we can do. So we know the principal amount, the initial amount is $2,000. 1 plus all of this stuff. I love my calculator to do the work for me. So I'm going to make this kind of calculator ready, and then I'm just going to go grab my calculator and do it. 7 times 360. And now I've got all the numbers in there. And now I'm just going to go to my calculator and get the calculator to do it. So I'm left with $2,838.06. Not bad investment at all. Our final example gives us an opportunity to graph inequalities and inequalities with exponential functions. So we will look at this function first. We'll look at the function y is equal to 2 to the x plus 1. We know that everything is going to be shifted up 1, translated up 1, if you will. And so instead of having the graph look something like this, where this is 1, the graph is going to move up here like this. And I'm going to use a darker mark to display that. So our graph is going to do something like this. And its asymptote will no longer be at 0, but the asymptote will be at y equals 1. And so we can expect to have, we could expect to have an asymptotic relationship here with the y equals 1 line. All right, so let's say this is 1, and here's our y equals 1 line there. And let's extend it over here like that. Halfway decent. You guys get the idea. And so that's what's going on. That's what our graph looks like. Shifted it up 1. But we realize that y does not equal that particular value. And when we have it not quite equaling it, it's just a boundary line. And so what we want to do is make this boundary line dotted. So this is a dotted exponential graph. And then we see that y has to be less than this, so we know that we're going to shade below for this problem. So we'll shade below the y equals x line, or the y equals 2x plus 1 line, or curve. You guys know what I'm talking about, right? All right, babies. Let me let you go. I look forward to talking to you soon. If this has been a little bit complicated, let me know, and I'm sure we can come together and clarify things. Take it easy. Bye-bye.